Hi everyone, my name is Ben Skinner. I'm here with the UTS Animal Logic Academy, and I'm going to be taking us through some of how we implemented our USD plugins and other pipeline specifics. So firstly, let's look at how we created a custom ArResolver in USD. So as some background, our ArResolver, or Asset Resolution Resolver, we were able to create this using USD's plugin architecture. They allow you to extend a lot of the core functionality. And asset resolution happens in USD when it encounters a file path. Now, most of the time this is an absolute file path on disk, but we needed it to work with our custom URI query. So our general overview for this was that we wanted to encode our asset information as a URI query. So down the bottom is an example of a typical USD document using references, and that's our URI query down there, and so that's how we wanted it to work. But as we were developing this, we came across some problems. The USD plugin that we had to create was C++ only. This was for a variety of reasons, but one of which was because the USD is multi-threaded, and so for performance reasons, Pixar enforced you to make this asset resolution plugin in C++. Contrastingly, our Shotgun Toolkit API was Python only. So if you don't have any kind of experience with Tank, it's essentially, there's no database behind it. It's just files on disk. However, through pattern matching and templates, it kind of resolves things back and forwards. But as mentioned, this was only Python, so somehow we had to make C++ and Python talk to each other. We kind of came up with three options. The first was that we could embed Python using CPython. This had some problems behind the scenes because of the global interpreter lock. It meant that it might become slower when it's really crucial that it's not slow. Another option was that we could have a central server and access it through a REST API. This had some problems. It was probably going to have to rely on, as mentioned, a central server, and so it could potentially become really slow. And if lots of people accessed it once, it'll really bottleneck the pipeline. And along with this, if that one server went out, we would have a devastating effect on production, as no one would be able to resolve their assets. Our third and final option was to use sockets to message between C++ and Python. This would require each artist workstation to start up and manage its own server, which again could be problematic if they went down and not knowing when they went down and releasing updates. But ultimately we were able to use the ZMQ library, and through that it really facilitated everything that we needed to do for this project. So it became our savior, and we were able to talk between C++ and Python relatively easy. So to kind of encapsulate our whole problem and solution domain, our main problem was that we couldn't talk between Python and C++. So the way we solved that was that on each artist workstation, we hosted a local Python server, which constantly listened for queries to resolve. And then each C++ client that we had, we connected that, we sent the URIs, it waited, and then once it received something, it continued as normal. For this, we made extensive use of the ZeroMQ library. It has a plethora of bindings, but for us, C++ and Python were enough. Here's the same example of a URI query that Wen mentioned before. You can see here that we kind of break it down, and there's different tokens which we pass along to Tank. This then gets fed into our Animal Logic Academy ArResolver USD plugin, which is where a lot of the code and development went into. And then it does its thing, it sends it off to the Python server, the Python server resolves the query, and then it sends it back to our C++ plugin. And so you can see down here, that's how we wanted to resolve it, and that path on disk would lead to the asset. So for some background on the Python side of things, and specifically the server, we needed it to run on every single artist workstation. This meant that it had to handle startup and shutdown. It had to restart if there were problems, but correctly log out for our sake. We also needed it to handle URIs. So the main kind of loop for that was that it would listen for a URI, it would resolve it if it found one, and then it would send it back to the sending C++ client. So some of the requirements that our ZMQ server had to handle was that there were a really high volume of assets that we were going to resolve. USD referencing can often be many layers deep, and so we needed to keep up with the default efficiency of USD. On top of that, we needed to handle messages from multiple threads. So as mentioned before, USD is inherently multi-threaded, and so we needed to make sure that we weren't adding any unnecessary delay. And also it needed to be invisible to artists so that behind the scenes, there'd be no connection or messaging. It would just kind of resolve really quickly and they wouldn't have to know. Our first version of our server was something along these lines. We had connected our C++ client via ZMQ sockets to a single worker thread in Python. But as we developed, we realized that we kind of needed a lot of different threads on the Python side of things to handle the volume of queries. So our second version of the server looks something more like this, where the C++ client would send it to the Python server, which would then have a pool of worker threads, which would then handle things as needed. Our initial results were really positive. Within one day, we were able to get the server and clients talking to each other, and then the same week, we connected it to our USD plugin and actually deployed it to our artist workstations. This was kind of really important because we had a really rapid development cycle, and so once we got it to our artists, we were able to then solve any edge case problems that might have arisen. And another really good positive was that the ZeroMQ library was very easy to work with, and their documentation really made it quite easy for us to implement. On the C++ plugin side of things, we kind of early on were able to separate out just the C++ ZMQ code because it was common between a couple of different C++ plugins we had to create. So for this, a big thing was our USD plugin, but we also had Katana custom operators and some other things as well. And so by separating out just the C++ ZMQ client code into a separate library, we were able to build both of these together against that and separate out the code. Our goals for the USD plugin was that it had to handle regular file paths normally, so absolute file paths would work. Along with that, it had to recognize our custom URI schema, which would then send it off in the appropriate way. It also had to work quite quickly and efficiently, again, not adding any overhead on the existing USD resolving time. And it also had to cache queries and resolve paths. This was something which was added later on in development when it became necessary, but we kind of came down to two different sorts of cachings that we needed. The first one was that we'd store it in memory for single sessions, where you might have 1,000 copies of the same object. There's no need to resolve the same object 1,000 times. The second form of caching was that we'd store it to disk, which meant that we could transfer it across different USD app sessions. But also when we started submitting things to the farm, we were able to package up the cache, and then we'd kind of have like a way to lock off different versions. So when a job to the farm was submitted, we sent that along. But again, I'll talk about this in more detail later. Solving it wise, we created the C++ client. That was done in our custom ArResolver constructor. USD side of things, we overrode the AR default resolver class, and there was a specific function, the resolve with asset info function, which was called every time USD encountered a file path. And so we were able to hook into that, and then if needed, we appended an asset cutoff time to the query, and then we were able to handle the query messaging as well as handling regular file paths. And some of the challenges we encountered was that it was hard to tell and give artists a way of knowing when their queries were finished resolving, or if there were any problems resolving, or if they wanted to restrict to specific asset versions. We didn't come up with a way of making a front end in that respect, but that's kind of something which would have to be more DCC specific as well, and potentially something we could build next year. On top of this, we initially had some ZMQ latency problems. A lot of these were solved when we went in and changed some of the ZMQ default settings. Specifically, the high watermark and low watermark were things which kind of made a difference for us. And our final challenge was kind of knowing how and when to flush caches, which brings us on to our final topic, query caching. So we decided to cache our ZMQ queries on the client side. This was done for a couple of reasons. We found in our early tests that a lot of the time spent from our plugin was spent making a connection, making a message, then sending the message, and then waiting for a response. We could have cached things on the server side as well, so that it wouldn't have to resolve things. But even if it had cached it on the server, it would still have to make that message and the connection between the two. So by cutting it off early and caching on the client side, we were able to solve a lot of those problems. As mentioned before, we had two ways of caching. We needed in-memory caching for specifically lighters, because they'd often be loading up a set and then doing multiple revisions of lighting renders. And so we wanted to just resolve the scene once and then let them do multiple renders. But then we realized that as they were submitting their jobs to the farm would have no concept of that cache. So what we did was we serialized the cache as it was in memory, put it onto a file on disk, and then when we submitted that farm job, we made sure that cache was there as well. And this kind of alleviated most of our issues, and again was able to provide some historical information about each render submitted, so that you would know which file was sent along with that render. Our initial results again were really positive. We did find that it was difficult to specify individual versions, and moving on from that was when do we cache things, and the idea of a latest asset or an approved asset or a latest approved asset. We kind of had a lot of mentorship from our leads on this at this point, but we decided as a whole that for us it was better to have a latest approved asset, so that the assets were more being pushed down the pipeline. Because we have such a smaller, relatively inexperienced team of artists, we just wanted to make sure that the art they were creating was getting seen as quick as possible and then fixed as quick as possible. Ultimately though, it works. The results from our pipeline can be seen in the work that we've created this semester, and we're really happy with everything we did. We've got here an example of a caching race just to kind of show the benefits. It's the same scene, and the scene only has 2 objects, but that object is then replicated. I think we got a couple thousand in there for this test. And if you want, you can write in the comments section down below which one you think will win. I think that's all I need to do. Without any further ado, let's get on with the cache race. So right off the bat here, we have disk and memory going. All of them have created a USD window, and there we go. As you can see, 4.133 seconds, we have the disk and memory cache going. You can see navigating the scene, and then followed shortly by just memory caching at 10 seconds. And then to no one's surprise at all, we have the last one where there's no caching at all. As you can see, we have a long way to go, and the no caching actually takes 1 minute 17. So that was fun. Our Katana plugin was also C++. We thought it was important to mention in this presentation because it also required our C++ client. We use this mainly for automated Lookfile assignments in Katana. If you've never used Katana, a Lookfile is basically a way of defining a material which can then be applied through Katana to different models and meshes. It kind of had the same challenges. The plugin had to be C++. There was no Python able to be used. The way we kind of then embedded the Lookfile URIs was that when each set piece or model was published from Maya, we embedded a Lookfile URI, exposed it in Katana via USD user properties, which are actually a really helpful part of USD, which allow properties to be transferred from application to application. And then our little node here recognizes that it has a custom user property, and then it does another query to our server to get the Lookfile it needs. Thanks so much for listening to this portion of our USD pipeline presentation. If you have any questions, feel free to let us know. We have a couple different social media accounts, and as well as where this video is being published as well. So thanks again. Make sure you check out the other videos in this series, and see you all soon.